Sound is our next topic that we're going to talk about. And the two major qualities that we need to consider when discussing sound is intensity and pitch. Now, intensity has to do with the amount of energy of the sound wave, and pitch has to do with the frequency of the wave, how quickly the wavelengths pass a given point. So amplitude is what we relate to the energy of a wave. So pitch is frequency and intensity is amplitude. Now remember that we measure frequency in hertz. So the pitch is also going to be described in terms of hertz. And we can say that the higher the frequency of a wave is, the higher the pitch will be. Now with pitch, we're looking at three different ranges here: ultrasonic, human range, and infrasonic, because we describe sound in terms of what we can hear. So human hearing has a range of 20 to 20,000 hertz. And so then we describe anything that's below 20 hertz as infrasonic. Now infrasonic means below sound. Now that's misleading because we're describing that sound wave based on what we can hear. Well, there are things that can hear below 20 hertz. So that sound wave is a sound wave for someone other than a human. We describe it as infrasonic because we can't hear it. And the same is true for the above 20,000 hertz. We describe above 20,000 hertz as ultrasonic. Ultra means beyond, so beyond sound. Now, again, that's in terms of our human hearing. We can't hear it, so we say it's beyond hearing. But there are animals that are able to hear above the 20,000 hertz range of a human. Now, just because the human range is from 20 to 20,000 does not mean that every human hears from 20 to 20,000. So you would have to get a hearing test completed on yourself in order to find out what your personal range of hearing is. Now, intensity, another word that we use to describe intensity is loudness. So loudness is our perception of intensity. When sound is really loud, we're actually describing the intensity. Now, we measure loudness as decibels, and I have a couple of things here to give you an example of that scale. So a whisper is 20 decibels, and a rock concert is 140 decibels. So from 20 to 140, we have a big jump. Now notice that the threshold of pain is 120. So when you go to those rock concerts and you leave with your ears feeling like they're full of cotton or they're ringing, then you know that you have passed your threshold of pain. Now let's talk about how we can change the speed of sound. The reason we're able to change the speed of sound is because sound has to have a medium to travel through. So if we change some of the qualities of the material that the sound wave is passing through, we will change the speed of that wave. Now, one of the first things we can do is change the state of matter of the object. Sound will travel fastest through a solid and slowest through a gas. And if you've ever watched any old westerns, you may have seen the country, the cowboys putting their ears to the railroad track to listen for the train. And actually that's good science application, because the vibrations of the sound from the train would travel faster through the train track than it would through the air. Now, when sound travels faster through a solid or a liquid than the gas that we're used to hearing it coming through, it will sound different to us and we won't be able to understand it. And I'm talking about words. So if you've ever gone underwater and tried to talk to your friends and you laugh about how funny you sound, the reason it sounds so funny to you is because your words are actually traveling faster through that liquid than they would the air that you're used to talking through. Now, density is another thing that we can change about the substance that the sound wave is traveling through. And density, remember, is about how tightly packed together the molecules are. So the closer the molecules are, the quicker the energy from one molecule can transfer to the other. So density allows sound to travel faster through it. An object with high density will allow the sound to travel faster. So iron is more dense than cork. Iron would have sound travel faster through it. And that's the reason we have some materials that we use as sound buffers or insulators, and we have other materials that we use to transfer sound for us. Now, elasticity is another quality that affects the speed of sound, and elasticity causes sound to travel faster through it the more elastic the substance is. Now, elasticity is a quality that students struggle with, so let me clarify what we're talking about here. If you've ever had the opportunity to run on pavement versus running on the sand of the beach, then you might have noticed that when you run on pavement, you can get a faster time. And that's because when your foot smacks the pavement pushes back. It does not give when your foot hits it. So it is what we call an elastic substance. Now, when you run on loose sand or loose snow, the sand or the snow will give way under your foot, which causes you to slow down because you have to, pick your foot back up before you make the next step. Now, that elasticity then, if you think of a rubber band, when we are describing elasticity, we're not talking about its stretchiness, we're talking about how quickly it snaps back. So elasticity, how quick molecules will snap back in place, is what makes sound go faster through the material. So metal is more elastic than cloth. Now, we have temperature here as our last speed factor. And the slower speed sound will be in the lower temperatures. Now, when you first look at that, it may look as if I have made a mistake because I said that sound travels slowest in a gas, and I've also said that it travels slowest in the coldest temperature. Well, the coldest temperature would be with the solid. So what you have to do here is you have to be careful to make sure that you're describing the same state of matter. So when I look at two substances in the same state of matter and I see their temperatures and one of them has a lower temperature than the other, then I would say in that state of matter for that substance, sound travels slowest through the one with the lowest temperature. We're going to start talking about some applications of sound now, and one of the biggest ones is the Doppler effect. And the definition of Doppler effect is that when at least one object moves, sound waves will be compressed and sound higher on approach, but they will stretch and sound lower when passing. Now notice that it does not say the object producing the sound has to be the thing that's moving. It only says that at least one thing must be moving. So when I have sound, the sound is coming from the blue dot, being knitted, sound waves will be produced around that object in 360 degrees and will stretch out in a regular pattern from the source of sound. So this is when the hearer and the producer of the sound are both stationary. Now, if either the sound begins to move or the person begins to walk toward the sound, what will happen is between the two objects, you will get a compression of the sound waves. The hearer will hear the first wave while the second wave is coming to him, and they will get crushed together. He'll hear the waves sooner because the sound is coming toward him. Now, on the back side, because the sound is traveling away, sound will stretch. it takes a longer time for the first and the second and the third wave to reach the ear of the listener. So we will have a longer frequency over here and a higher frequency over here. So high frequency equals high pitch. So on this side it will sound high pitched, and on this side it will sound low pitched. If you think about your experience with sirens passing you, like an ambulance or a police car on the side of the road, you'll know the application that we're talking about here. Now, we do have an opportunity then to catch our sound. And so if the object travels as fast as its sound that it's producing, it will stay with its original wave. It's traveling with that first circle. We call this the sonic boom. Now you do have supersonic jets, and what they do is actually travel faster than the speed of sound. So you will see the supersonic jet in the air first, and then you will hear the sound that comes from his travel. All right, now here are some other applications of sound. We have acoustics, which is the study of sound. Echolocation, which is using sound to locate objects. Sonar, which stands for sonic navigation and ranging. And then the ultrasound, which uses sound to create an image of an interior structure. Now, acoustics is what we use when we are producing the concert halls and our music rooms. We want to make sure that we get a good sound quality in the room. Now, echolocation and sonar are closely related, and what we do here is we use sound waves to locate objects. We can have echolocation in animals use this, and we also have devices like when we want to go deep sea fishing. We have an echolocation device or a sonar device that will produce sound waves and be reflected back. It'll hit an object and bounce back, and when it does that, it lets us know that there's something under there at that depth. Ultrasound in the medical field allows us to see the images of our unborn children. It will also be used to identify clots in the circulatory system. So all of these things are applications of sound.